Okay, welcome back. I was discussing about Boolean algebra and we have already gone through the three basic premises or laws or operations, whatever you call it, that is AND law, OR law and NOT law. That is these three operations. We have already learned it. We have also learned, how to create the truth table. Today we are going to, continue further with our discussion on, truth table. Here what we are going to do is we are going to understand how to find the logical combination of a Boolean expression. For example, what do I mean by that? Say for example, I have an expression of this sort, say a plus b dot c complement. I have an expression with the following content. Now what does it mean? Plus means OR, we have already seen this in the last class. Dot means AND, we have already seen this in last class. And NOT, the bar represents NOT. It may be either a bar or a complement. So a plus b dot c complement. In any Boolean expression, just like mathematical expressions, there is a procedure, or rather there is a method for operation. Like in mathematics, a simple numerical mathematical expression, we follow the BODMAS system. So here also we follow a certain rule for evaluating a Boolean expression. And what are the rules? First, please remember, the parenthesis should be evaluated first. So first, number one, it's the parenthesis. That is brackets. So any contained within the brackets should be evaluated first. This is the first thing, which is also applicable even for mathematical expressions. Second is the NOT operation. The NOT operation should be done first. Next, the AND operation should be done at the next level. And lastly, you should go for the OR. So we'll follow the parenthesis first, then NOT, then and lastly OR. So that should be the precedence of operation in a Boolean expression. Precedence of operation. Precedence of operation in a Boolean expression. So what are the steps? First, all the parentheses contained should be evaluated. Next, the NOT operation should be performed. Next, and lastly OR. So here I have a Boolean expression. Now what I'm going to do is we are going to see the different possible outcomes of this particular Boolean expression with the help of a truth table. This is what we are going to see. So here you can see there are three Boolean variables A, B and C. So we'll take three variables A, B and C. So you may consider this to be the inputs. A, B and C may be considered to be the inputs. Let me draw a straight horizontal line out here. Now there are three inputs. So three inputs, you must be remembering last day I showed you the technique of creating a truth table. That is 2 to the power 3 is 8. Half of that will be 0 and half of that will be 1. So half of 8 is 4. So 4 zeros and 4 ones. So this is in the first column. Now next is half of 4, that is 2. So 2 zeros and 2 ones. And then half of 2 is 1, a single 0 and a 1. Now, next, according to the precedence of operation, which should be evaluated first, the NOT. And here we have C complement. So that's the NOT operation. So we are going to do that first. So C complement we are going to first find out. And the NOT operation is simply negating or reversing the inputs. That is 0 becomes 1 and 1 becomes 0. I believe you remember the negation. That is why it's also called the inverter. I believe you remember. So 0 becomes 1, 1 becomes 0, and that is how the entire thing goes. So this is what we get with C complement. Next, we'll go for the AND operation. So next is the AND operation. AND is symbolically represented by dot. I believe you remember that. So B dot C complement. So this two columns should be ANDed. So B dot C complement. So this two we are going to AND. In an AND operation, remember, when all the inputs are 1, then the resultant is 1. So in the first row, you can see 0 and 1 is 0, 0 and 0 is 0, 1 and 1 is obviously 1, 1 and 0 is 0, 0 and 1 is 0, 0 and 0 is 0, 1 and 1 is 1, 1 and 0 is 0. So this is what we get with B dot C complement. Next, what is left is OR operation. That is OR this with A. So this two should be ORed. A plus B dot C complement. B dot C complement. So this should be ORed. So let's try it in OR. Remember, either of the inputs are 1, then the resultant is 1. So 0 or 0 is definitely 0. 0 or 0, once again 0. 0 and 1 is 1. Again 0 and 1. 0 and 0 is 0. And here all the 4 are 1. So it doesn't matter what is out here. So 1, 1, 1, 1. So this is the resultant what we get for the Boolean expression out here. So we have seen what is the resultant output we get in terms of 1s and 0 for this particular Boolean expression. So this is what we can do with a truth table, that is finding the outcome of a Boolean expression. Now this may also be applied for proving a Boolean expression. For example, I'll give you an example with respect to this. Okay, and now what we are going to do is, we are going to try proving this particular expression, A plus A complement dot B equals to A plus B. So we have, two expressions at the left hand side and right hand side. What we are trying to do is prove that, suppose you get a question like that. So what we are going to do is, we are going to apply truth table, the technique which we had learned while using a truth table to prove this particular expression. So we are going to try with this. So here what do we have? A and B. A and B are the two variables which we have. And remember the different combinations for A and B, that is 0, 0, 1 and 1. And then for B, 0, 1, 0, 1. Next, we are going to write the expression for A complement. Remember, the NOT should be done first. So 0 becomes 1, 0 becomes 1, 1 becomes 0, again 1 becomes 0. Then A complement dot B. So this two should be ANDed. So A complement dot B. And remember, when all the inputs are 1, then the resultant is 1. So here we have 0, here we have 1, here we have 0, here we have 0. And then what we are going to do is, we are going to try out A plus A complement dot B. That will complete the left hand side. A plus A complement dot B, that is A or A complement and B. So this two should be ORed. So let's try this. So 0 or 0 is 0, 0 or 1 is 1, 1 or 0 is 1, 1 or 0 is 1. So that's what we get from the left hand side. Now on the right hand side, what do we have? We have A plus B. So for A plus B, what do we have? We are going to OR this two. So 0 or 0 is 0, 0 or 1 is 1, 1 or 0 is once again 1, 1 or 1 is 1. So you can see these two columns are exactly same. These two columns are exactly same. So hence we can tell that the expression is proved. So you see how simple it is possible for us to prove using a truth table. Pretty simple, I believe. Now what we are going to understand is drawing logic circuits. Now we need to understand how these logic circuits are created. Now before doing that, what we are going to do is, we are going to learn something called the logic gate. Okay, here what we are going to learn is logic circuit. Logic circuit is basically an electronic circuit that is used to implement a Boolean expression. We are just learned how to draw a truth table for a Boolean expression. So here also logic circuit is actually physically implementing this particular circuit. So this is what we are going to learn with logic circuit. But before that, what we are going to do is, we are going to understand something called the logic gate. So the question arises, what is logic gate? Logic gate is basically a electronic component. Basic electronic component that implements a Boolean logic by taking some inputs and giving some outputs. So depending upon the inputs, we'll get different type of outputs depending upon which Boolean logic am I talking about. So based upon this, we have three very basic logic gates. So first of all, the AND gate we are going to learn, just like we had learned the AND logic or AND operation first. So symbolically, when we draw it, it will be something like this. Now this is not the physical component. Physical component is it's created using a transistor that you'll study in physics. How to implement the AND gate. Here what we do is we simply draw a D, and then we have these are the inputs. You can put an arrow to indicate that. You may have two or more than two inputs, because AND, it is possible for AND to perform more than it can take more than two inputs. So you may have two inputs or more than it. However, you will get a single output. So this is the logical diagram for the AND gate. This is what we do. So you can tell, suppose this is A and this is B. So this is obviously A dot B. So this is A and B. You may have even three inputs. It doesn't matter, because it is possible to take two or more than two inputs. Suppose these are three inputs. You will always have only a single output. So A, B, C. That means there are three inputs, and this is the output A, B, C. So actually it means this. This is what we do. We don't write it this way. Each of the outcome results we don't write. But at least for understanding, I'm just showing you how to do that. Next comes the OR gate. Okay. How do we draw the OR gate? OR gate is drawn this way. So here we have two inputs, say A and B, and the resultant output is A plus B. This is what we do with OR gate. And then we have the NOT gate. The NOT gate is something like this. It's altogether a triangle with a circle before it. Here we have a single input and a single output. So if this is this is A complement or A bar, either way you can write. So look at the way we draw the different logic gates. Now using this, we are going to design a logic circuit. Logic circuit is used to implement a Boolean expression using logic gates. So what is a logic circuit? It's a circuit that implements a Boolean expression using logic gates. So that is what we are going to do while drawing a logic circuit. I'll give you an example. Now suppose we are going to draw the logic circuit. Suppose we have a Boolean expression something like this: A plus B complement dot C. So what I am going to do right now is draw a logic circuit corresponding to this particular Boolean expression. So how do we draw? Now you see there are various methods or techniques for drawing. Please remember, the way I am going to show you is the most standard method. Everywhere, whenever you go for even higher studies, you will be learning or you will be utilizing only this method. So please be used to with the method which I am going to show you out here. So A, B, C are the three variables. So A, B, C, we write it this way, and then we draw vertical lines. So please draw vertical lines this way. And next, what we do is, out here, we have to do the NOT operation first. Remember the precedence of operation. What were the precedence of operation? First was NOT. Of course, before all that, we had the parenthesis. Then the second was NOT. Thirdly, we had and lastly, we had OR. So here we are going to do this. These are, you can just imagine it to be wires. So we have three wires. The input is coming from here. First, we are going to go for NOT. NOT means we are going to draw the NOT gate out here. Here what we can do is we can make a disconnector over here. So how we can draw that? Suppose this is the line, straight line which was here. So we can make a disconnector. This is called a disconnector. That means it's only connected to B. So this is how we draw. If you draw straight, that means you are connecting it to both B and C. That might be a possibility. But in this case, since it is only B naught, that means we are not going to connect it to C. So symbolically it is drawn this way to indicate that it is not connected to C but only to B. Next, what do we have? AND it with C. So here once again, from C I am going to draw a line, and with B complement I am going to make an AND gate because it's B complement and C. So here we are yet to get the result because after that we need to OR it with A. Now from A, what we are going to do is we are going to bring one more connector. However, it should be disconnected from B and C. And then what do? We'll OR it with A. So this is what I'm going to do. So here, if we define it properly, B, this means it is B complement because this is the NOT gate. And out here, what was the resultant? This B complement was the input for and this is the C, which is the input. So what do we get? B complement dot C, and this B complement dot C is the input for this OR gate, and one more input is this A. So we can tell A plus B complement dot C. So this is the logic circuit. Pretty simple, isn't it? Okay, I'll show you one more example of implementing a logic circuit. So I'll try out one more logic circuit. Say for example, we have a logic circuit with the following contained: A plus B. I'm applying a parenthesis, and then we have B complement dot C plus A, making it quite complex. Now what I'm going to do is, first please remember what are the variables out here: A, B, C. There are only three variables. So first of all, we'll take A, B and C and draw vertical lines. And remember, you don't put arrows throughout the entire circuit. It is not necessary. Only during the input at the top level you can put the arrows to indicate that those are the input signals. Next, what do we have? We can start with this particular parenthesis, that is A or B. So from here we take a connection, disconnect with B, disconnect with C, and this is what we get. B, from B we connected, however disconnect with C and OR it. So this is what we get. So what did we get? This is actually A or B, that is A plus B. No need of writing that. Next, we are going to perform the operations given in this particular parenthesis. Within this parenthesis, we have B complement, that is NOT gate is to be evaluated first. So what we are going to do is we are going to start from here, B complement, and then AND it with C. Because AND needs to be performed before OR. And lastly, with this resultant, we are going to OR it with A. So here from A, we are going to bring out a wire, disconnect with B, disconnect with C, bring it out here. And what do we have? OR operation. So we are going to do the OR operation. And then we can bring the line a bit here. Don't make a huge, logic gate. Some of you have the habit of making a huge AND gate. Just, pull the wires this way. It looks better. And then ultimately what do we have? This operation, this OR operation and this OR operation should be ANDed out here. So here we'll have an AND gate. So this is how the entire operation is performed. So I believe you understood today's the entire lesson. So what did we start with? We started with creating truth table to evaluate a Boolean expression to get the different type of resultant what we get. That was the first thing. With that we were able to prove Boolean expressions. We tried out one or two proving using truth tables to prove that. Later on we are also going to learn how to prove things algebraically. Even that is there within our syllabus. And then we learned different type of logic gates, of course based on only those three basic logics, that is three primary logics: AND, OR and NOT gate. That is what we learned. And finally, we understood how to perform the create the logic circuit. And remember the precedence of operation for both truth table and logic circuit. That is first parenthesis, then NOT, then and lastly OR. Okay, welcome back. In the previous class, what you had learned was, you had learned how to create a truth table corresponding to a Boolean expression. We had also learned, how to create a logic circuit using the different gates. I believe you remember that, and you must be, practicing with the assignments which I have already given. In this class, we'll do opposite to what we had learned prior to this class. That is, what we are going to do is, we are going to find the Boolean expression corresponding to a truth table. We had found the truth table corresponding to a Boolean expression. This time just the opposite. I'll make a random truth table and try to find the corresponding Boolean expression to it. And while doing so, there are, several steps involved which we are going to understand. Instead of, slowly telling you the different steps, we'll directly start with it and you will slowly get the concept very clearly. So this time what we are going to do is, we are going to learn finding the Boolean expression from a truth table. So this is what we are going to try now. Suppose, let me take a random, truth table. Suppose I have this truth table A, B and C, and this is the output C. And for 3 inputs, remember 8 combinations, so 4 zeros, I believe you remember that. 4 ones, again 2 zeros and 2 ones, again 2 zeros and 2 ones, again a single 0 and a 1, a single 0 and a 1. So this is what we get, for a 3 input. These are the combination. Now the output which I am writing is simply randomly I am writing. I am not following any sequence. I am just randomly writing. So these are the possible outputs. I have just randomly written. There is no, clue to it or anything of that sort. What I am writing over here. Now what we are going to do is, before finding all this, that is finding the Boolean expression which leads to this particular truth table, we are going to understand 2 terms. That is something called the min term and the other one is called the max term. These are the 2 terms which we are going to understand. What does it mean? In min term, what we do is, we find the AND operation for each of the Boolean variables. And how do we do that? And for max term, we'll find the OR operation for each of the Boolean variables. So how do we do it? For min terms, what we are going to do is, for every time you get a 0, please remember, we'll have the variable as complement. So what do we get? This is A complement dot B complement dot C complement. This is what we get. For here, for this particular thing, what I'm trying to do is, whenever I get a 0, I'm putting a complement. Whenever it's 1, I'll keep the variable as it is. So in the second case, it will be A complement dot B complement dot C. In the third case, again the same thing, that is 0 will become complement dot, again 1, so this will remain as B dot C complement. Fourth case, A complement dot B dot C. See how I'm writing this? In this fifth case, 1 0 0, so what do we have? A dot B complement dot C complement. In the sixth case, A dot B complement dot C. Next, in the seventh case, that is A dot B dot C complement. And lastly, what do we have? All are 1, so A dot B dot C, so no complement. So very simple, we followed a very simple technique that whenever we got a 0, we put a complement corresponding to that variable. And whenever we get a 1, we keep the variable as it is, and the entire thing is ANDed. So for min terms, we always AND all the terms. For max term, what we are going to do is we are going to OR all the terms, but this time if it is 0, we'll leave it as it is, and only when it is 1, we are going to put a complement to it. This is what we are going to do. Let's see how we do this. So 0, 0 and 0. So what do we have? We have A plus B plus C. So this is what we are going to do. And here again A plus B plus, now you see this A plus B, this is fine, but when it is 1, we'll put a complement to make it C complement. So this is just the opposite to the functionality of what we had learned for min terms. And here for the third case, it's A plus B complement plus C. For the fourth case, again A plus B complement plus C complement. Again for the fifth case, it's A complement plus B plus C. For the sixth one, it is A complement plus B plus C complement. For the seventh one, what do we have? We have A complement plus B complement plus C. And lastly, finally, what do we have? A complement, because all are 1, B complement plus C complement. So this is how we find the min terms or max terms. Now, what we are going to do is to find the Boolean expression that corresponds to this particular truth table. I am just trying to explain you. You don't have to write everything whenever you find the Boolean expression. I am trying to explain you these terms. Now what we are going to do is we are going to find the Boolean expression corresponding to this particular truth table. So there are two methods of finding it. One is called the sum of product, SOP, sum of product. The other one is called product of sum. So what we are going to do is, let me draw a line to separate the entire thing. We are going to find the sum of product as well as product of sum for this particular truth table. Very simple. To find the sum of product, we'll see the min terms and we'll only use those min terms whose output is 1. We'll keep it that simple. We are going to write all those min terms whose output is 1, which are again odd because it is sum of product. Product here means and sum means OR. So each of these products we are going to add it up. So how do we do that? In sum of products, what did I tell you? We are only going to see those min terms whose output is 1. Remember, for sum of product it's 1 and for product of sum it's 0, which you have to see. So for sum of product, what we are going to do? Look at this. First, what do we have? We have 1 for A complement dot B complement dot C complement. So we'll write that A complement dot B complement dot C complement. So that's the first term. And since this is sum of product, this is the first product, we are going to sum it. That is OR plus, which is the next one. The next one is out here. And what is the min term that corresponding to it? So A complement dot B dot C. So we have A complement dot B dot C plus, which is the next one we have out here. So what do we have? A dot B complement dot C complement, which is the next one. This is the next one. So we have A dot B dot C. So this is the entire Boolean expression for this corresponding truth table. If you make a truth table for this particular Boolean expression, you will get exactly this output. Same thing what we can do is for the product of sum. In product of sum, we are going to check for those max terms whose output corresponds to 0. Remember, only those max terms whose output corresponds to 0. So what I'm going to do, we are going to write the first 0 is out here and the corresponding max term is this. So A plus B plus C complement. So A plus B plus C complement. So don't forget the bracket parenthesis out there. And then what do we have? We have the next 0 out here, that is A plus B complement plus C. The next 0 is out here, which corresponds to A complement plus B plus C complement. And then we have one more 0, that is A complement plus B complement plus C. So this is what we get. So you see how simply we were able to find out the sum of product or product of sum expression for a corresponding truth table. Now you don't need to find the min term or max term for each and every variable. Whatever the question is requirement, that is if I ask you for sum of product, you only look at those outputs which are 1 and find the corresponding min terms and write it out there. Similarly for the max terms, you do exactly the same thing. You check only those outputs which are 0 and write the corresponding max terms associated with it and add it. That is what you are going to do. I'll give you an example related to this. Now I'm going to show you an example where we are going to find the Boolean expression both with respect to sum of product as well as product of sum. So suppose you get a question something like this: find the SOP and POS expression for the corresponding truth table. So what we are going to do is, I'm just going to give you the truth table, that is A, B, C, and these are the outputs. So and I'm writing the output simply randomly. Okay, now what I'm going to do is find the sum of product and product of sum expression corresponding to this particular truth table. So first of all, we'll go for the sum of product expression. In sum of product expression, what do? We only look at those outputs whose resultant is 1. So here we have this. We have a 1 out here, so we are going to find the corresponding min term to this. And what is the corresponding min term? Wherever it is 0, it becomes complement. That is A complement dot, this is B dot C complement. Because what I am trying to do is, I am just going to, if this becomes complement, 0 becomes 1. B is already 1, that is why we keep it as it is. C, which is 0, again I make it complement to make it 1. So 1 dot 1 dot 1 is definitely 1. Hence we write it this way. Next, plus. Next we go for the next one. And what do we find? A complement dot B dot C. So here we have A complement dot B dot C. And for the third one, remember, if it is 1, keep it as it is. For 0, just complement it. So A dot B complement dot C complement. And lastly, we have one more 1 out here. So what do we get? A dot B dot C complement. Please look at this carefully. A dot B dot C complement. This is how we get the sum of product expression corresponding to this particular truth table. Now what we are going to do is, we are going to find the product of sum expression. So how do we do that? For product of sum expression, remember, it all depends upon how the question is given. If they ask you to find sum of product or product of sum, it will actually, they will ask you only a single one, either sum of product or product of sum. So if they do not ask you, they just ask you to find the Boolean expression, you can find either of them. However, if they ask, you have to find exactly that. So for product of sum, what do? We look at those outputs which are 0. And then we OR the Boolean variable so that the resultant is 0. So what do we have? 0, 0, 0. So it will remain as it is. Please remember, these are max terms. Whenever we use the product of sum, we use max terms, and in max terms, what do we have? If it is 0, we keep it as it is, and if it is 1, we simply complement it. Okay, for the product of sum expression, what we are going to do? For product of sum expression, we are going to look at those outputs which are 0. So here we have the first 0. For the first 0, remember, if it is 0, we will keep it as it is. That is, we have A plus B plus C followed by the next 0, that is A plus B plus C complement followed by this 0, that is A complement, because it's 1, A complement plus B plus C complement, and finally we have all that as 1. So A complement plus B complement plus C complement. That is what we are going to do to find the product of sum expression. Hope you understood the entire thing. Thank you.